This is the Chapter 13 homework for Physics 102A, starting with number 61. We have a mass of ice at 0.120 kilograms, and we're going to break this down into step 1, taking the ice from negative 25 degrees to 0 degrees, and then step 2 is going to be melting the ice into water. So I've divided these up into the two different steps, so you can see the heat of step 1 is the mass times the C of ice times delta T. So we plug in those numbers, and remember that the specific heat of ice is different from that of water, so we get 2090 joules per kilogram Celsius degrees. Change in temperature is 0 minus negative 25 degrees, so that gives us a change in T of plus 25. And the heat for step 1 becomes 6270 joules. For step 2, it's a phase change. So since it's going between solid and liquid, we use the heat of fusion, L sub F. So we take the mass times the heat of fusion, 3.33 times 10 to the 5th joules per kilogram. And we get the heat for step 2, 39,960 joules. When we add those up, the heat from step 1 plus the heat from step 2, we get 46,230 joules. Number 63. We have a mass of copper at 15 grams. So we break that up into the two steps. The first is the phase change, bringing it from liquid to solid, which means we're going to use the heat of fusion. The second step is the temperature decrease, going from the melting point. You can look that up in the book. That's at 1084 degrees Celsius, bringing it down to 600 degrees Celsius. So for step 1, notice here I've included the negative sign. You're going to have to insert that because you have to realize that we're removing heat. So Q of step 1 is negative m times L of F. So we have the mass of 0.015 kilograms times the heat of fusion of copper, 2.05 times 10 to the 5th. So we get the heat removed for the first step is 3,075 joules. For step 2, this is the temperature change. So it's mass times specific heat of copper times delta T. So 0.015 kilograms times 385 times the change in temperature, which is 600 minus 1084, and that gives us a negative quantity, 2795 joules. Then when we add up the heats, making sure that they're both negative, Q1 plus Q2, we get negative 5870 joules. The question is asking how much needs to be removed. So the negative tells us that heat is removed, but a proper answer would be that 5870 joules is removed. Number 65. This is a power question. We'll deal with power in the end. But first we recognize that power is heat divided by time. So we recognize that we have to solve for heat. We're dealing with 52 kilograms of copper. Initially at 20 degrees we want to melt it, which means in step 1 we have to bring it up to 1084 degrees Celsius. Then once it's at its melting point, then we're going to melt it from solid to liquid. So I've written this out in the way that I did for y'all in class. So heat equals the heat of step 1 plus the heat of step 2, mc delta T for step 1 and mLF for step 2. Then we plug in the numbers. I've broken it down here into the heats of the different steps. So for step 1 it becomes 2.13 times 10 to the 7th joules. For step 2 it becomes 1.066 times 10 to the 7th joules. And so the total heat is 3.196 times 10 to the 7th joules. Now we answer the question related to power. If power is heat divided by time, That means that time is heat divided by power. You can algebraically solve for that. We solve for the heat, 3.196 times 10 to the 7th joules. We divide by 120 times 10 to the 3rd watts, and we get a time of 266 seconds. Number 67. .410 kilograms of water at 11 degrees Celsius, and we want to turn it into ice at negative 14 degrees Celsius. That's going to involve 3 steps. The first step is to take the water from 11 to 0. The second is to change the water into ice. And the third is to take the ice from 0 to negative 14 degrees Celsius. Since we're removing heat, we recognize that all 3 of these terms, Q1, Q2, and Q3, should come out negative. So, for heat of 1 and heat of 3, since those are temperature changes, we're going to do MC delta T. But be careful, in step 1, it's water. So for step 1, we're going to use the specific heat of water, 4186 joules per kilogram Celsius degrees. Whereas for step 3, at that point, it's ice. And so we need to use the specific heat of ice, which is 2090 joules per kilogram Celsius degree. Also be careful when you do delta T. As I've always reminded you, delta is final minus initial. So in step 1, that's 0 minus 11 Celsius degrees. And in step 3, it's negative 14 minus 0, so negative 14 Celsius degrees. You can see at the bottom of the screen, I've divided it up into the heat amounts for the 3 parts. So part 1, part 2, and part 3. You can also see that by far most of the heat removed was in step 2, which is turning it from liquid to solid. That's not always universally going to be the case. That wasn't the case for number 65, the previous problem. Part of that was due to the fact that it was such a massive change in temperature that we had to do. But in this problem, you can see those different heats, and you add them all up. Again, recognize that each of them is negative. So you add them all up and you get negative 167,000 joules approximately. And the question is asking how much heat must be removed. So we can say 167,000 joules.